Hey everyone, so this is the video solutions to Worksheet 6.4. We're going to go ahead and be working with logarithmic equations and inequalities in this one. We're going to start off with number one with some equations. So for part A, we're asked to solve for x if the log of 3x minus 1 is equal to the log of 4 minus x. Now a couple things we want to remember, since we're dealing with logarithmic functions, there's a very specific restriction that we have on what we can put into logarithmic functions, namely that we can only take the log of positive numbers. So one thing that we may want to consider, and you don't have to do this every time, but maybe making some domain acknowledgments as you work through this. So we could look at this and say that, well, if I'm taking the log of 3x minus 1, I know that 3x minus 1 has to be strictly greater than 0 in order for me to count that as a solution. Otherwise, I'd be plugging in a 0 or a negative number. So we could solve this really quickly for x. We've got 3x has to be strictly greater than, let's try that again, has to be strictly greater than 1. And then we divide both sides by 3. X has to be strictly greater than 1/3. So whatever values for x that we may come up with in this equation, it better be something greater than 1/3. We also want to check this other logarithmic function in this case. We'll do the same sort of setup. We'll let 4 minus x needs to be some number strictly greater than 0. If we subtract 4, we get minus x, strictly greater than negative 4. We divide both sides by negative 1 or multiply by negative 1, and we get x has to be less than positive 4. So, excuse me, when we get to our solutions, we want to make sure that any solution we come across fits into these restrictions for x. Okay, so now we can go ahead and we can actually solve this equation. So one thing you're going to want to note in this case is you're going to come across different types of logarithmic equations. This one has just logarithms in it, so there's no constants or anything floating around. So the technique that we're going to use to solve this is going to be slightly different because it's just logs. So here we note that we have just logs, so just logarithms. We're going to see that if we have constants, we're going to take a slightly different approach than we do here. So one thing that we may notice is that if the log of 3x minus 1 has to be equal to the log of 4 minus x, then what would have to be true is that 3x minus 1 would have to be equal to 4 minus x. That's the only way that that equation is going to be balanced. So when you have two logs, you get to use this type of approach, which is pretty simple for the most part. So now we just have to take this and solve for x. So if we add x to both sides and then we add 1 to both sides, we get 4x is equal to 5, which means that x is going to be equal to 5/4. Now it is imperative in logarithmic equations that we double check these answers, because it's very common to get superfluous solutions or extra ones that we don't actually get to use because of restrictions. So we want to check that 5/4, which is 1.25, 1 1/4, is a number greater than 1/3, which it is, and it's also a number less than 4, which it is. So since this checks with both of our restrictions, we can work with that. So we always want to check this is a solution. Now if you don't have to make these domain restrictions from the beginning if you don't want to. You could always just find your solution or solutions and then try plugging them back in to your original logarithmic functions just to make sure that it's still a positive number. So however you want to do it is up to you, but that's definitely one way. Okay, so now we come across one in part B where we've got the log base 3 of 7 minus 2x is equal to 2. So what we're going to want to note here is that we have logs and constants. So note there are logs and constants. Now in this case what you want to do is you want to get your logarithmic function on one side, so one log on one side and constants all to the other. So just like how we have it set up. So they did all the work for us to start. Here we've got one log on one side, we have a constant on the other, and then we can go ahead and we can solve appropriately. Again, I'm just going to make a quick note here that 7 minus 2x has to be strictly greater than 0. And if we solve for x, we subtract 7 from both sides, divide both sides by negative 2, and we notice that x has to be some number less than 7/2, so less than 3.5. All right, so having done that, let's go ahead and solve this. Now, we need to get rid of this log to get at the x. There are a number of ways you could do this. Some folks might say, well, using the inverse properties of logarithms and exponentials, I could make both sides exponents of my base, which is 3, which will cancel out the log. That's one way to think about it. Another way to consider it is we think about how we defined a logarithm with respect to the exponential function. We know that if we have the log base b of x, and that's equal to a, then b to the power of a has to be equal to x. And then this is something that we can solve for. I'm going to go ahead and I'm going to use this this property to solve this. So we look at this, and since we've got a log equal to a constant, we can go ahead and say, well, this implies that 3 to the power of 2 has to be equal to 7 minus 2x. Well, we know that 3 squared is just going to give us 9. And then we've got a very simple linear equation that we need to solve for x. So go ahead and we'll subtract 7. So we'll get 2 is equal to negative 2x. And then we'll go ahead and we'll divide both sides by negative 2. And then this gives us the solution that x is equal to negative 1. Again, we're going to want to check this with our original problem. Negative 1 is a number less than 7/2, so we're good to go. And if we wanted to, we could just plug negative 1 in to our original log, and we noticed that we'd be taking the log of a positive number, so we'd be in good shape. So those are the two different scenarios that we're going to run into. Either we have two logs, log on one side, log on the other. We equate the arguments like we did in part A, or we're going to get a log on one side and a constant on the other, and then solve however we need to. That's what we see here in part C. So we've got a log and a constant. So I'm going to go ahead and I'm just going to translate this using this property in green above. So the base here is 10. So this tells us that our inner argument x has to be equal to 10 to the power of 5.4. And that's a perfectly good solution. I mean, unless we're asked to round this, this is what we would call an exact solution. And in general, we would probably just want to go ahead and use that unless we're asked to specifically to round to a certain number of places, or to take it out to a certain number of places. So that's going to be our answer for that one. Now, of course, we'd want to double check that this actually fits in to our domain here. So this is a positive number. So if we're taking the log of this solution, we'd be taking the log of a positive number. So this solution would check out. Then we can go ahead and we can hop down to part D, which is very similar, except we've got negative log of x is equal to 5.4. So first thing we want to do is we want to isolate the log. Now that would mean that if there's any coefficients floating around or extra constants, we'd want to get everything to the other side. So isolate the log. In this case, we'd have to multiply both sides by negative 1. So we have log of x is equal to minus 5.4. And then we just use the same property. So this tells us that x has to be equal to 10 to the power of negative 5.4. And this is it's a very small positive number, but it's a positive number. So this would work out if we did substitute it back in to our equation, because here our only restriction is that x would have to be strictly greater than 0. So that checks out. All right, now when we get to part E, this is a slightly trickier one. We've got a couple of logs. We also have a constant. So this sort of falls under the heading of logs and constants. So we're going to get one log on one side and a constant on the other side. Now that means that we're going to need to use properties of logs to combine these two together. So we've got the sum of two logs with the same base, so we can combine them as a product in the argument. So we've got the log base 5 of the product of our two arguments, which would be 2x plus 1 times x plus 2. And we're going to go ahead and just multiply that out now, just to save us some time later. So it's going to be 2x squared plus 4x plus 1x, which would be 5x plus 2. So now we can go ahead and take this over, and we now have one logarithm, the log base 5 of 2x squared plus 5x plus 2 is equal to 1. We use our properties of logs to turn this into an exponential equation. So the argument 2x squared plus 5x plus 2 will be equal to 5, our base, raised to the power of 1. Or in other words, we've got 2x squared plus 5x plus 2 is equal to 5. So now we've got a pretty straightforward quadratic that we need to solve. So we're going to solve this for x. Let's subtract 5 from both sides, which will give us 2x squared plus 5x minus 3 equals 0. We could use the quadratic formula, or we could see if this factors. In this case, it does factor rather nicely. So we've got 2x, we've got x equals 0, and the numbers that are going to work for us here is we'll go ahead and we'll use positive 3 and minus 1. Using the zero product property here, we know that either 2x minus 1 has to be equal to 0, or x plus 3 has to be equal to 0. These imply possible solutions of x equals 1/2, or x is equal to negative 3. Now the question now becomes is, well, are both of these valid solutions? Well, let's see. We could either plug them in to our original logs, or we could just go back and maybe determine the restrictions. Let's go ahead and see. This particular one, I'll do this in green. This log tells us that 2x plus 1 has to be greater than 0. So that implies, if we subtract the 1, divide by 2, that x has to be strictly greater than negative 1/2. And then this one tells us that x plus 2 has to be greater than 0, or x has to be strictly greater than negative 2. So taking both of these into consideration, we'll take a look at our solutions. Well, this one says x equals 1/2. Well, 1/2 is greater than negative 1/2, and it's also greater than negative 2. So we're going to go ahead and we're going to keep this one. This one checks out. Notice that if we put negative 3 in there, negative 3 is not greater than negative 1/2. It is not greater than negative 2. So we would actually ditch this one. So here's a situation where our a possible solution turns out to not work out for us, and the only one that we'd want to use is this one. This happens quite often when you have to use properties of logs to solve these equations like we did here. So you always want to be careful for those. So this one's a fun one. So we've got the ln of x is equal to 3. Well, let's go ahead and solve this like we normally would. Let's not get too intimidated. We'll look at this and we'll say, well, I've got a log and a constant. You know, let's just forget about the fact that we've got the ln of x. We've got the natural log of something, some function of x is equal to 3. Now we remember that the ln of x is the same as the log base e of x. So our base is e. So if we solve this, we're going to say that I'm going to write it like this, just to make it a little more clear. So we've got the log base e of, I'm just going to leave this as the ln of x because we don't have to worry about this just yet, is equal to 3. So using properties of logs, the inner argument here, which is the ln of x, coincidentally, has to be equal to the base of the log, which is e, raised to the power of 3. Now we're not quite done solving for x. Just like up here in this step, after we set up our equation, we still had a lot of work to do to solve for x. We still have work here to do to solve for x. In fact, we have another logarithmic transition to make. So we have the ln of x is equal to e to the 3. Well, this is the exact same thing as the log base e of x is equal to e to the 3. E to the 3 is just a number, so we can say that our argument x is equal to our base, which is e, raised to the power of this number on the other side of the equal sign, which just happens to be e to the 3. So we've got x equal to e raised to the power of e raised to the power of 3. Now this is definitely a positive number, and that's going to work out just fine. And here we can plug this in, so this one checks out. A little bit tricky, but we just basically had to make two conversions from logarithmic to exponentials to solve that. Okay, so now we move on to number 2, and we're going to be doing logarithmic inequalities. So just like the other inequalities that we've done, we're going to want to go ahead and find zeros or critical points and set up a sign diagram to solve for these. I'm going to look at this, and I'm going to make a quick call here for part A. I know that my x's have to be greater than 0. So one thing that we can consider at this point is that when it does come time to come up with our solution intervals, that we don't even need to bother worrying about values less than or equal to 0, because the only possibilities here are x values greater than 0. So this is a nice thing to reduce the scope of our sign diagram later on, and we'll see how that works. Okay, so step 1, let's go ahead and convert this let's get 0 on one side of our inequality. So I'm just going to go ahead and I'm going to rewrite this as the log of x minus 5.4 is less than 0. So once we've done this, let's go ahead and we'll find our zeros. So to do that, we're going to go ahead and take this equation here. We're going to set it equal to 0 and then solve for x. So to solve for x, we'll go ahead and we'll take the log of x. We'll move the 5.4 back over, which kind of seems silly, but it's important to get this for later on. And then we'll go ahead and we'll convert this into an exponential. So we know that x is equal to our base, which is 10 to the power of 5.4, because this is the common log. So here's our 0, which helps us for our third step, which is to construct a sign diagram. So we construct a sign diagram, and while we're at it, we can interpret our inequality. So let's go ahead and get started with this. So normally we'd construct a sign diagram, we'd go from negative infinity to positive infinity. However, we know that the only x's we're interested in are x's greater than 0 because of the log of x from the original inequality. So we can start our sign diagram going to infinity and then starting at 0. Now we can never include 0 because we couldn't plug it in, so that's why we're setting up the sign diagram like this. And then we've got our 0 that we want to plot on here. So that's 10 to the power of 5.4. So I'm just going to go ahead and slap that down right here. So 10 to the power of 5.4. So that's a pretty big number. So now we're going to go ahead and we're going to pick test points. So I'm going to go ahead and just pick 1 from this one, and I'll pick I don't know, 10 to the power of 8. That's a number bigger than 5.4. So we'll pick those as our 2 test points, and then we'll test them into our function, which is on the other side of that 0 on our inequality. That's why we needed to take that first step. So if f of x is equal to log of x minus 5.4, for testing point purposes, we'll go ahead and we'll test f of 1, and again that would give us the log of 1 minus 5.4. We know that the log of 1 is just going to be 0 minus 5.4, so that tells us that on this interval this function would be a negative number. And then we'd go ahead and we'd test f of 10 to the power of 8. So we've got the log of 10 to the power of 8 minus 5.4. And evaluating this log, since it's base 10, we'd find out that that's just going to be 8 minus 5.4. And that's going to give us a positive number. So now we can make those notes on our sign diagram. So this is a negative interval. This is a positive interval. This value is a 0 of our function. So now all we have to do is we have to interpret. Now we wanted to find out, based on this, when is this function, which we just tested values for, strictly less than 0? Well, it's going to be strictly less than 0, not at 0, not at our 0, but in between on this negative interval that we determined. We don't include the points because we can't include 0, and we can't include 10 to the power of 5.4 because it's strictly less than. So this tells us that our interval, our solution interval, would be from 0, non-inclusive, to 10 to the power of 5.4, non-inclusive. And that would be our answer. Okay, so let's go ahead and try this same setup on this next one. So I'll leave the directions up, or the steps. So step 1, we want to get 0 on one side. So let's go ahead and have 0 is less than, we've got log of x minus 2.3. Okay, so again, what I want to keep in mind as we start testing points and things, this is our function. We'll just call this f of x. That's our function that we're testing to see when is this greater than 0. All right, so step 2, we're going to go ahead and we're going to find our zeros. And if we do that, we'll take our function, which is log of x minus 2.3. We'll set it equal to 0, and we'll solve. So we get log of x is equal to 2.3, which tells us that x has to be equal to 10 to the power of 2.3. And again, we get the 10 because this is the common log, or the log base 10. So there's our 0. Now all we have to do is in step 3, we set up our sign diagram and interpret the inequality. So I think we can lose that now. So again, we look at this and we see, well, x has to be strictly greater than 0. So for our sign chart, we can start at 0, go off to infinity, and we're going to plop down our other point, which is 10 to the power of 2.3. So we know that this is a 0 of our function, so we'll mark it as such. And now we'll test points. So let's go ahead, and again, I'm going to pick 1, and since we already used it last time, we'll pick 10 to the 8 because we know what happens when we take the log of it. So we test f of 1 in our function f of x, so that's going to be equal to the log of 1 minus 2.3. That's going to be equal to 0 minus 2.3, which is going to yield a negative number. And if we test f of 10 to the power of 8, we get the log of 10 to the power of 8 minus 2.3, which is going to give us 8 minus 2.3, which will yield a positive number. So now we can go up to our sign diagram, negative interval, positive interval, interpret. What do we want to know? Well, we wanted to know, back here in step 1, when is this function greater than strictly 0? So that's going to be this interval right here. So we can't include our 0 because it's strictly greater than, but then we'll include all of this all the way off to positive infinity. So the result is the interval from 10 to the power of 2.3 all the way off to positive infinity. That would be the solution to this inequality. Okay, now luckily the work that we've done for A and B is going to pay off in this next problem, part C. So we've got a triple inequality here. When I see triple inequalities, I like to just break these up into 2 individual ones and think about them individually. So I'm going to see this and say, well, I've got 2 different questions going on here. I want to know, when is the log of x strictly less than 5.4? And I also have the inequality, when is the log of x strictly greater than 2.3? Now, if we didn't already know the answers to these, we'd have to solve 2 inequalities, just like we did for A and B. Luckily, we've already done that. So we know from part A, that our solution here is going to be the interval from 0 to 10 to the power of 5.4. And then we know from part B that our solution here is going to be the interval from 10 to the power of 2.3 all the way off to infinity. Now with these triple inequalities, what we're looking for is if there's an overlap here, we want that intersection. So in this case, we want the intersection of these two intervals. And I think this will be more clear once we put this on the real number line. So intervals. Essentially, we're looking for the overlap. All right, so let's go ahead and see what we mean by this. So if we were to draw out the real number line, first of all, we know that we're kind of stuck at 0, and we're going off to positive infinity again because we look at our function log of x, and our x values can only be greater than 0, so we just ignore the other side of the real number line here. Now let's go ahead and plop down our two intervals. So we've got a couple points here. So we've got 10 to the power of 2.3, and then a little further down the line we've got 10 to the power of 5.4. So one of our intervals that we've got here, I'm going to star this one as green, is from 0 to 10 to the power of 5.4. So that's from 0 all the way up to 10 to the power of 5.4. So there's one of our solution intervals that would work. But not only does it have to satisfy this inequality, we also have to satisfy this inequality, that x, log of x has to be greater than 2.3. That would leave, I'll put this in blue, that would leave this one. And we know the solution here would be 2.3 off to infinity. So the overlap here would be this interval. So this is the intersection. And this is going to be the solution to this inequality. So our solution to this original inequality in part C would be from 10 to the power of 2.3 to 10 to the power of 5.4. And that would be our answer. So we're lucky that we already did parts A and B. Otherwise, we would have had another 2 inequalities to have to solve in the same manner that we did for part A and for part B. Okay, so that does it for the solutions to section 6.4, and I will see you all in the next video.